My name is Lara. I'm the head of the R&D department in Esteyco, and today I'm going to present you all Esteyco's concrete technologies, both for onshore and offshore wind. I'm going to start with a very brief introduction about who we are, and we are leaders in onshore wind, to later move to explain about our offshore technologies, both for fixed and floating platforms. Well, Esteyco is an independent Spanish civil engineering consultancy and architecture consultancy firm founded in 1970. During these almost 50 years, we have carried out plenty of projects and studies, both nationally and internationally, related to civil engineering in different areas such as road and railway, water engineering, environment, urban planning, and energy infrastructures. With regard to wind energy, 20 years from now, we initiated our roadmap in this sector by studying the pathologies that were already appearing in existing wind towers. With that purpose, we founded a specific department of energy projects, and since then, we are participating not only in wind, but also in hydropower and solar plants, liquefied natural gas storage tanks, and we have recently got involved in the ITER experimental fusion reactor project in France. So now focusing in the wind energy sector, we must highlight the work that we have been carrying out in foundation design, where we design more than 1,000 units per year, and where we have come to develop our own patented technology, which we call braced foundation. You can see it in the picture up on the right. This is a new foundation, which is lighter than the conventional ones, which can reach savings of around 40–50% in concrete and steel, and around 30% overall. We also perform geotechnical campaigns and the complete civil works of the wind farms, access roads, drainage, and so on, allowing us to offer a comprehensive service, which is what developers demand today, a full wrapped package. 10 years ago, and again, based on our structures expertise, we identified an opportunity in the market and developed the first precast concrete wind towers of greater capacity and height, a worldwide pioneer technology which is currently being employed at an industrial scale in large wind farms. Concrete is the material traditionally used in civil engineering to reach increased heights of more than 160 meters, as compared to current steel limit about 100 meters, although this is also growing too. With precast manufacturing, production rates compatible with the wind industry, demands are easily attained. And designs of these kind of towers can be found in the list of the wind farms that are on in the slide. Well, so it is logical that with that expertise we gained within the onshore sector, we thought about how to move to the offshore one. And the result of this was the development of the ELISA technology for bottom fixed platforms and the floating technology for floating ones. So now moving to the bottom fixed platform. Well, the ELISA technology is based on two concepts: a telescopic tower configuration, allowing for both self-transportation and self-installation of the complete wind turbine to be fully assembled onshore, and a gravity-based foundation used also as a temporary self-buoyant platform with virtually no extra cost. Each unit is made of concrete, fully assembled onshore, turbine included, and conventionally towed to the site. And on top of this, the key novelty of the technology is its independence of heavy lift vessels during the installation. Here it is worth noting that these are novelties in the offshore wind industry, but not at all in the civil engineering. The strand jacks used for the telescoping system are, for example, used also in the bridge engineering, and concrete cations have been floated and synced by hundreds a year in a similar way as we do with our GBS, merely using harbor tugboats. So, as I said, the whole set is manufactured and assembled in harbor, including the turbine. It is towed with conventional tugboats to the final site, and with the aid of an auxiliary system, is ballasted to the seabed. The tower sections are then lifted with the stranjacks, and the whole system is ready to operate. And of course, as seeing is believing. And just to rest a little bit, let's see a video of the ELISA technology. Clarify how is the. This is the foundation of the construction, the GBS. The telescoping tower manufacturing by precast pieces, which are also transported by conventional means to the place where is the installation. These are the Tailwind lifting tests that we performed on harbor just to test all the system. The turbine installation onshore. This is the installation of the auxiliary system that we use to ballast the GBS once it is in the final position. This is the coupling of the ring. The towing with just merely tugboats. It's actually one doing the towing, and the other one is just supporting just in case. Ballasting. Well, epic music for an epic task. The prototype is already producing energy and it's operating in the island of Gran Canaria. But all of this we have just seen is very nice if the project is bankable. And in order to achieve this, it is essential to do the validation and the certification of the technology with a renowned certifying body. And in that sense, the whole process has been duly certified. The design basis, the conceptual design, the onshore prototype of the telescopic tower, and the ultimate design and full-scale prototype in Gran Canaria. Certifications have been achieved with DNVGL and TÜV, and although the last one have certified the full-scale prototype in Gran Canaria, we received an Offshore Innovation Award prize granted by DNVGL. The resulting advantages of what you have just seen in the video are summarized in the slide. Significant cost reduction compared with actual fixed technologies, full inshore assembly, complete independence of heavy lift vessels, mass production, local content, and so on. Now moving to the floating platform, to the Tailwind technology. The concept consists in what we call an evolved spar, in which the typical long mast is substituted by a lower tank suspended by tendons from an upper base, which sufficiently lower the system's center of gravity below its center of buoyancy. The system acts as a solid rigid since the tendons are arranged in a triangular way, and when the bottom weight is displaced laterally due to external action, its own weight provides the recovery moment, which tends to return the structure to the upright position. So from this base upwards, the concept is the same as in the sister ELISA GBS technology. With this configuration, the general manufacturing and installation process is similar to the one we have already seen in the video for the GBS. The difference is that the lower tank is not ballasted to the seabed, but that is filled with a certain amount of solid ballast prior to towing, and then with water is ballasted to its final position with the tendons in tension. Afterwards, the mooring is connected and the whole system is ready to operate. The Tailwind technology is 2-3 years behind the ELISA technology when we talk about TRL. The outcome of the Tailwind project funded by the European Commission is that shown on the slide. We developed the technology from conceptual to detailed design for a 5 megawatt wind turbine, the scalability for a 12 megawatt. We carry out the model basing test and also the laboratory test for the suspension tendons, the CAPEX and OPEX estimation, both for single and serial production, and the design certification. The project finished last December 2018. However, since then, we have kept on evolving the design, which is shown on the right picture. Those are the last drawings. And just to conclude today, we would also like to introduce to you an O&M technology we are currently developing, which evolves from the auxiliary floating system we used to ballast the Helicam prototype, that yellow platform that we saw in the video. This platform consists in mounting the coupling ring of that system to a conventional barge, which can host an also conventional crane. The set is attached to the substructure via the ring, and the onshore crane can operate to carry out large corrective maintenance tasks. This ATOMS project has been recently funded by the European Commission to complete the development and full demonstration of the technology in real operative offshore conditions. and we will take advantage of our LISA 5 megawatt demo unit currently operating in the Canaries to perform that offshore validation. So just in short, we are confident that this ATOMS technology shall be pioneer in allowing for vessel-free large corrective operations, and that shall also provide an option for floating platforms, which is still a key unsolved technological challenge unless the unit is fully disconnected, power and mooring, and brought back to port. And that was all about Esteyco's technology. Thanks all for your attention, and sorry for those minutes.